Good morning and welcome to our final lecture. I hope you've made use of the previous 2 weeks to either read the lecture notes or watch the videos that I prepared for you. This week we're going to finish talking about calculus. We will talk about the most important theorem in calculus, the fundamental theorem of calculus. We will see an interesting technique called the substitution method. And then, as an application of calculus, we will calculate the area between curves. In past lectures, we've been talking about an integral as a limit of Riemann sums, but we don't want to have to set up a Riemann sum and then take the limit every time we want to calculate a definite integral. We want a better way. We want an easier or quicker way. We have a very important theorem, in fact the most important theorem in calculus. If you only memorize one theorem about calculus, then it should be this one. Suppose that we have a continuous function defined on a closed interval. The theorem has two parts. The first part of the theorem says that the function defined in this way, that capital F of x is the integral from a to x of f of t dt, is continuous and differentiable. And the theorem says that the derivative of capital F is equal to small f. In other words, capital F is an antiderivative of small f. Moreover, if instead of this antiderivative we have any antiderivative of small f, then we can calculate the definite integral of small f of x between a and b by just calculating capital F at b minus capital F at a. Two important ideas to remember. Often students remember the second part, but they forget the first part. I want to do some examples using the first part of the theorem first. For example, I want to find dy dx if y is given by the integral from a to x, t cubed plus 1 dt. And by the theorem, the derivative of this function, all we do is we take the integrand t cubed plus 1, we replace t by x, and we get the answer, x cubed plus 1. Another one. Find dy dx if y is equal to the integral from 1 to x sine t dt. To solve this problem, we just take the integrand sine t and we replace sine t by x. So we just get the answer sine x. Here's another one. This one looks difficult, but it really isn't. Find dy dx if y is equal to the integral from 0 to x of sine of the natural logarithm of tan of e to the power t squared. We have this very, very complicated function. If we wanted to, we could try to calculate this integral first and then differentiate it, but that would be a silly way to solve this problem. Instead, all we're going to do is we're going to take this integrand and we're going to replace t by x. The answer is just sine of the natural logarithm of tan of e to the power x squared. Let's start making them a little bit more difficult. Find dy dx if y is equal to the integral from x to 5 of 3t sine t dt. Now, in the past, we've been doing d dx of an integral from a, and then at the top we had x. But we don't have this now. Now we have our x at the bottom and a number at the top. First, so that means we need to do an extra step. We need to change our integral so that it looks like the integrals we've been doing so far. But that's not a problem. We know we can swap the positions of x and 5 if we add a minus sign. We're calculating d dx of minus the integral from 5 to x, 3t sine t dt. And then we use the theorem. We just replace t by x to get the solution minus 3x sine x. Let's make this a little bit more difficult again. Find dy dx if y is equal to what? The integral from 1 to x squared of sine t dt. To solve this one, we're going to need to use the chain rule. To use the chain rule, we need to choose a u. We're going to choose u is equal to x squared. Then we use the chain rule. The chain rule says dy dx is dy du du dx. We have the integral from 1 to u of cos t. We know how to do this. We'll just replace t by u. And then we're multiplying this by the derivative of u, or in other words, the derivative of x squared. And we know this this is 2x. So we get cos u multiplied by 2x. Substitute in x again, and write it a different way around. The answer is 2x cos x squared. So that was part one. Part one told us how we can differentiate an integral. Part two of the theorem tells us how to calculate the definite integral of f. There's two steps. First, we find an antiderivative. That's any antiderivative, doesn't matter which one, just any antiderivative of our integrand. And then we're going to calculate capital F of b minus capital F of a. Because we're going to be writing this a lot, it's useful to have a short notation. Instead of writing capital F minus cap of b minus capital F of a, we're going to write square bracket f of x, square bracket from a to b. For example, the integral from 0 to pi of cos x dx. Remember, we always use radians in calculus. An antiderivative of cos is sine, because the derivative of sine is cos. So we have sine x calculated at 0 and pi. That means sine of pi minus sine of 0, or 0 minus 0, or 0. Another one. The integral from minus pi over 4 to 0 of sec x tan. We know an antiderivative of sec x tan x. We look back to our previous chapter about derivatives of trigonometric functions. And we can see that this is the derivative of sec x. So in other words, sec x is an antiderivative of sec x tan x. Then we put the numbers in, and we find that the answer is 1 minus root 2. One more. The integral from 1 to 4 of 3 over 2 square root of x minus 4 over x squared. We need an antiderivative of 3 over 2 square root of x. That's straightforward. X to the power 3 over 2 is an antiderivative of 3 over 2 root x. And then we need an antiderivative of minus 4 over x squared. We know how to do this. We know that 4 divided by x is an antiderivative of minus 4 over x squared. So we're calculating x to the power 3 over 2 plus 4 over x between 1 and 4. First, we use the top number. We use 4 to get 4 to the power 3 over 2 plus 4 over 4. And then we use the bottom number, the 1, to get 1 to the power 3 over 2 plus 4 over 1. Four to the power 3 over 2. We can think of it like this. We can think first we'll do 4 to the power of a half, and then we'll cube it. In other words, we're going to do 2 cubed, or 8. And you can check that the final answer to this problem is 4. We may be interested in the total area under a graph. If we say that all area between a function and the x-axis is positive, then we have something called total area. For example, let's first look at the function x squared minus 4. And I'm interested in this between minus 2 and 2. We can calculate the integral of this function between minus 2 and 2. You can check that we get minus 32 over 3. If we say that all area is positive area, if we make minus 32 over 3 a positive number, we get the total area is 32 over 3. Another example. This time, let's suppose we look at 4 minus x squared. Again, I'm interested in the total area between minus 2 and 2. We can calculate the integral of g between minus 2 and 2, and we get 32 over 3. This is already a positive number, so we can use this number for our total area. The total area between this graph and the x-axis is 32 over 3. Let me show you the pictures. On the left, we have the first function we looked at. This blue part shaded is the integral. This is 3. But if we say all area is positive area, then the area of this blue region is plus 32 over 3. And on the right, we have the function multiplied by minus 1, 4 minus x squared. This blue region represents the integral, and because the integral is positive, it's also the total area. For example, let f of x be sine x. Calculate the definite integral of f over the closed interval from 0 to 2 pi, and calculate the total area between the graph of this function and the x-axis over this interval. Here's a graph of the function. We're interested in the region which is shaded red. We want to calculate this definite integral, and we want to calculate the total area shaded red if we say that all area is positive. But first, from the graph, we can say we have a positive bit and we have a negative bit. If we let these be positive and negative, when we calculate the definite integral, these should cancel out and we should get 0. But if all area is positive, When we calculate the total area, we should get a strictly positive number. So let's do the calculations. First of all, the integral from 0 to 2 pi sine x. We can go through the calculation, and as expected, we get 0. The total area, we had two parts of the graph. We had the first part between 0 and pi, and then we had a second part between pi and 2 pi. We're going to look at these separately. We'll integrate between 0 and pi, and because we know this is going to be a positive number, we can just leave it as it is. We're going to integrate between pi and 2 pi. From the graph, we can see this is going to be a negative number, so we're going to put absolute value signs around this to turn it into a positive number. Then when we run through this calculation, and I'll leave this for you to check, we get the answer 4. The total area shaded red in this picture is 4. Let's summarize. To find the total area between the graph of a function and the x-axis, step 1, we need to divide our interval at the zeros of f into smaller pieces. And on each one of these smaller pieces or subintervals, we're going to calculate the integral of f. And then finally, step 3, we're going to add together the absolute values of these integrals. For example, find the total area between the graph of y is equal to x cubed minus x squared minus 2x and the x-axis for x between minus 1 and 2. We're going to choose this for our function. Let f of x be x cubed minus x squared minus 2x. First, we need to know where is f equal to 0. So I start by calculating f of x is 0 and factorizing the polynomial. You can check that this is equal to x multiplied by x plus 1 multiplied by x minus 2. How can we make this 0? Well, x could be 0. X plus 1 could be 0. In other words, we might have x is equal to minus 1. Or we might have that x minus 2 is 0. In other words, x is equal to plus 2. So we have our interval between minus 1 and 2. And we're going to break this up at these points. The function is 0 at minus 1, at 0 and at 2. So we're going to cut our interval into 2 at 0. Then we'll have two smaller subintervals between minus 1 and 0 and between 0 and 2. First, between minus 1 and 0, we can calculate this integral. This is not a difficult integral. You can check that we get 5 over 12. And then we calculate our integral between 0 and 2. Again, you can check that we get minus 8 over 3. So we have our function like this. Our integral of the red part was 5 over 12. The integral of the blue part was a minus 8 over 3. But we want this to all be positive. We want to add the absolute value of 5 over 12 to the absolute value of minus 8 over 3. 5 over 12 plus positive 8 over 3 gives us 37 over 12. The total area, which is shaded red and blue, is 37 over 12. We can also talk briefly about the average value of a continuous function. Let me remind you, if we had a discrete set of numbers, let's say 1, 2, 3, 6, and 9, we can calculate the average of these numbers by adding them together and then dividing by how many numbers we have. 1 plus 2 plus 2 plus 6 plus 9. And because we have 5 numbers, we do divide by 5. And we get equal to 4. Using the same idea, we can calculate the average value of a continuous function. Now, we don't have discrete numbers, we have a continuous function, so instead of adding the numbers together, we calculate the integral. Remember, integral means limits of Riemann sums. So we're doing sums, we're adding things together, and then we're taking the limit. The idea is the same. And instead of dividing by how many numbers we have, instead we divide by the width of the interval. Or you can just remember that this is the formula. The average value of f between a and b is 1 divided by b minus a multiplied by the integral from a to b of f of x dx. For example, find the average value of the square root of 4 minus x squared between minus 2 and 2. First, we calculate the integral of this function. I'll leave this for you to check that we get 2 pi. And then we use the formula for the average value of f, 1 divided by b minus a, or 1 divided by 2 minus 2, multiplied by this integral that we've just found, and we get that the average value of the function is pi divided by 2. Here's a graph of this function, and here the red line is the average of this function. The way to think about this is if we cut just here and here, roughly half of the function is above the red line, by which I mean roughly half of the domain, the function is above the red line, and roughly half of the function is below the red line. Find the average function value of x cubed minus x between 0 and 1. We have our formula. The average value of g is 1 divided by b minus a, integral of g, which for us is 1 over 1 minus 0, integral from 0 to 1 of g of x dx. I will leave it for you to check that if we do this calculation, we get minus 1 over 4. Before I finish this chapter, let me just remind you about the differences between indefinite integrals and definite integrals. Remember that an indefinite integral is a function. For example, the indefinite integral of x is x squared over 2 plus c. And the indefinite integral of cos x is sine x plus c. A definite integral is different. Definite integral, it has a similar name. It's just two letters shorter name. And the notation is similar. We just have this extra a and b. But this is not a function, this is a number. A definite integral represents a number. For example, the definite integral between 0 and 1 of x I was saying an infinite integral is a function, but a definite integral is a number. For example, the definite integral between 0 and 1 of x dx is a half, and the definite integral between 0 and pi over 2 of cos x is equal to 1. Chapter 33 is about a technique called the substitution method. What is the substitution method? Well, think about it like this. By the chain rule, we know that d dx of u to the power n plus 1 over n plus 1 is the same as u to the power n du dx. So therefore, the integral from u to the power, the integral of u to the power n du dx is the same as u to the power n plus 1 over n plus 1 plus c. But we also know that the integral of u to the power n du is equal to the same function. So these two must be the same. So it looks like du is the same as du dx dx. This is the idea behind the substitution method. For example, let's suppose we want to calculate the integral of x cubed plus x to the power 5, 3x squared plus 1 dx. We can use a substitution to change this into an easier integral. What we do is we start by choosing a u. For this integral, I want to choose u is equal to x cubed plus x. Then the idea of the substitution method is du is equal to du dx dx, which for us is 3x squared plus 1 dx. So we can do the substitution. Instead of x cubed plus x to the power 5, we have u to the power 5. Instead of 3x squared plus 1 dx, we have du. What we've done is we've changed a difficult integral into an easy integral. And as soon as we have the easy integral, we can calculate that this is u to the power 6 over 6 plus c, and then to finish, we substitute back in to get the answer 1 over 6 x cubed plus x to the power 6 plus c. Let's do another one. Find the integral of the square root of 2x plus 1 dx. Again, I want to use a substitution to change this into an easier integral. So I look at the integrand and I see there's a 2x plus 1 there. I'm going to let u be 2x plus 1, and then I'm going to see if that works. Does that change our integral into an easier integral? We calculate that du is the same as du dx dx, or 2x. Now we don't have 2x here, but we do have dx. So I'm going to do one extra step. I'm going to divide by 2 to get dx is equal to half du. And then I'm ready to do my substitution. Instead of square root of 2x plus 1, I have square root of u. And instead of dx, we know that this is a half du. So we can replace this by half du. Then we changed our difficult integral into an easy integral. All we want to do is calculate a half integral of u to the power of a half du. We know how to do this. This is a half u to the power 3 over 2 divided by 3 over 2 plus c. Substitute x back in and simplify. We get the solution 1/3, 2x plus 1 to the power 3 over 2 plus c. Let's write this method as a theorem. First of all, let's be careful. If differentiable function of x. If this function maps from the real numbers to some interval I, and if f is a continuous function defined on this interval, then the substitution method says the integral of f of g of x multiplied by g prime of x dx is equal to the integral of f of u du. This is the idea we've been using. Let's do another one. Find the integral of 5 sec squared 5t plus 1 dt. We look at the integrand and we want to choose a u to make this easier. I look at the integrand and I see there's a 5t plus 1 here. I'm going to choose u is equal to 5t plus 1. And then I can calculate du is equal to 5 dt. I'm ready to do my substitution. 5 dt is the same as du. Sec squared 5t plus 1 is then the same as sec squared u. We've changed our difficult integral into an easier one. We can calculate this. Recall that the derivative of tan is sec squared, so tan is an antiderivative of sec squared. We have tan u plus c. Almost finished. This is not the final answer because the final answer should have x in, so it should have t in. So we substitute back in again. We replace u by 5t plus 1 to get the final answer, tan 5t plus 1 plus c. Find the integral of cos 7 theta plus 3 d theta. We need to choose a u. The integrand has a 7 theta plus 3 in, so it makes sense to choose this for u. Then du is equal to 7 d theta. I don't have 7 d theta, I only have 1 d theta. So I'm dividing by 7 to find that d theta is 1 divided by 7 du. Then I'm ready to do the substitution. Our hard integral is equal to 1 over 7 integral of cos u du, which we know how to do. Let me move on to the next one. Find the integral of x squared sine x cubed dx. Again, we start by choosing a u. So the first sentence of our answer is about u. Let u be equal to x cubed. Then du, which by this method is the same as u dx dx, is equal to 3x squared dx. Let's look back at the integral. What do we have? I have an x squared, yes, I have a dx, but I don't have a 3. So I'm going to divide by 3 to get my formula. 1 over 3 du is equal to x squared dx. And then I'm ready to calculate the integral. I'll leave it for you to check that if we do the substitution, calculate the integral, and then substitute back again, we get the answer minus 1/3 cos x cubed plus c. This one's a little bit more difficult. Find the integral of x square root of 2x plus 1 dx. We need to choose a u. So we look at the integral, we have an x just here, and we have 2x plus 1. It makes sense to choose u is equal to 2x plus 1. Then we do our substitution as before, and we find that our hard integral is the same as the integral of x square root of u, a half du. But wait a minute, something different has happened here. We still have an x here. We can't do our integral yet because we have both x and u. We need to change all of the x's into u's before we can do our integral. How can we change this x into a function of u? Well, what do we have? We have that u is 2x plus 1. Rearrange this. A half u plus 1 is equal to x. What we're going to do is we're going to take this and substitute for x. In other words, the integral that we're trying to calculate is the same as the integral of a half, u minus 1, square root of u, a half du. And this is now an easy integral because this is equal to a quarter integral of u to the power of 3 over 2 minus u to the power of a half du. I would leave for you to check that the answer to this problem is 1 over 10, 2x plus 1 to the power of 5 over 2, minus 1 over 6, 2x plus 1 to the power of 3 over 2 plus c. Pause the video or read your lecture notes and check that you're happy with this calculation. Find the integral of 2z divided by the cubed root of z squared plus 1 dz. We start our answer by choosing u. Makes sense to choose u as z squared plus 1. Then we do our substitution and we find our answer. Again, read the lecture notes or pause the video. Check you're happy with this. We can also use the substitution method to calculate the integral of sine squared x dx. But we need an extra step. First, we're going to use an identity. One of the common trigonometric identities is that sine squared x is equal to 1 minus cos 2x divided by 2. So our integral is the same as a half integral of 1 minus cos 2x. To calculate this, we need to do a substitution. We're going to let u be equal to 2x. I haven't shown all the details here. You can check that we get the final answer, a half x minus a quarter sine 2x plus c. Similarly, and I'm leaving this for you to do, calculate that the integral of cos squared x is a half x plus a quarter sine 2x plus c. That was the substitution method for indefinite integrals. We also have a substitution method for definite integrals. And the idea is the same, except there's one extra thing we need to change when we do our substitution. We need to change the limits of integration. After we do our substitution, instead of integrating between a and b, we're going to be integrating between new numbers, which are g of a and g of b. Let me show you how we use this. Calculate the definite integral from -1 to 1 of 3x squared square root of x cubed plus 1 dx. I'm going to solve this in two different ways. First, we're going to use this theorem. We can start using the same idea we were using earlier in this chapter. We start by choosing a u. In this case, we choose u is equal to x cubed plus 1. Then du is equal to du dx dx, or 3x squared dx, just as we've done before. But here comes this extra step that we need to do. We need to say if x is equal to -1, put -1 in here, -1 cubed plus 1, you get that u is equal to 0. And x is equal to 1, replace x by 1, and you get 1 cubed plus 1, or u is equal to 2. Then we have everything that we need to do the substitution. Square root of x cubed plus 1 becomes square root of u. 3x squared dx becomes du. Instead of the lower limit being x equal to minus 1, the lower limit becomes u is equal to 1. And instead of the upper limit being x equal to 1, the upper limit becomes u equal to 2. We've changed our difficult integral into an easy integral. We can calculate this, and you can check that we get 4 square root of 2 divided by 3. Before I go on, you don't need to write x equal to here. You could just write minus 1 just here if you wanted to. You don't have to write u equal to 0 here. If you wanted to, you could just write 0 here. When I do this type of integral, I like to write x equal to u equal to, so I don't get confused as to what I'm doing. But you don't have to do this if you don't want to. If you think that you won't get confused, then it's okay to just write minus 1 and 0 here. Now I'm going to solve this problem using a different method. What I'm going to do is I'm going to do 2 steps. First, I'm going to find the indefinite integral. I'm going to use that to find an antiderivative of the integrand. And then in step 2, I'm going to calculate the definite integral that we want. So first, the indefinite integral. Again, we start with a substitution. Let u is equal to x cubed plus 1, and therefore du is 3x squared dx. So our indefinite integral is 2/3 x cubed plus 1 to the power of 3 over 2 plus c. That means that an antiderivative of our integrand is 2/3 x cubed plus 1 to the power of 3 over 2 plus c. And therefore, our integral is equal to 2/3 x cubed plus 1 to the power of 3 over 2, evaluated at minus 1 and 1. And again, we can calculate that this is 4 square root of 2 divided by 3. What are the differences between these two methods? In solution 1, we did a little bit extra work at the start, but then the end of the calculation was easy. This one, we've skipped the extra work at the start, but then we have to do a little bit extra work at the end when we're calculating. Some integrals, one method will be easier, some integrals, the other method will be easier. Or it's completely up to you which method you choose to use. Calculate the integral from pi over 4 to pi over 2 of cotan theta cosec squared theta d theta. We need to choose a u. There's 2 possible options here. We might choose cotan theta, or we might choose cosec theta. You could try both to see which works. I know that the one which works is choosing cotan theta. But just there's no obvious way to decide this. It's just try them both and see which one works. Let u be cotan theta. Then du is minus cosec squared theta d theta. Take the minus sign across. Minus du is cosec squared theta d theta, which is what we want. We have a cosec squared theta d theta. We're going to replace this by minus du. We're going to do a little bit extra work at the start. If theta is pi over 4, then u is cotan pi over 4, which is equal to 1. And if theta is pi over 2, then u is cotan pi over 2, which is equal to 0. We're ready to do our substitutions. Instead of theta equal to pi over 2, we replace this by u equal to 0. Instead of theta equal to pi over 4, we replace this by u equal to 1. Instead of cotan theta, we replace this by u. And instead of cosec squared theta d theta, we replace this by minus du. We have the easy integral minus the integral between 1 and 0, u du, which we can calculate is equal to a half. Chapter 34, the final chapter of this course, is an application of integrals. We're going to be looking at the area between curves. Let's suppose we have two functions, the function f and the function g. And let's suppose we're asked to calculate the area shaded blue between these two curves. When we do this, we're doing total area. We want all area to be a positive number. What is the total area which is shaded blue in this picture? We have a definition, we have a formula. At the start, I'm just being careful. The formula is that this area is the integral from a to b, bigger function minus smaller function. For example, find the area between y is equal to 2 minus x squared and y is equal to minus x. Look at the picture. Which function is the bigger figure, which is the higher one? The top one is 2 minus x squared, and the bottom function is y is equal to minus x. So it's going to be 2 minus x squared minus the bottom function, so minus x. There's something else we need from the picture. We need to know where are we integrating between. What is this number circled in orange, and what is this number circled in orange? First, we're going to find these two numbers. These two numbers marked with a question mark, which I circled in orange, occur when the graphs intersect. In other words, they occur when 2 minus x squared is the same as minus x. We can do our calculation, and we can find that these numbers must be minus 1 and 2. That means we're going to integrate from minus 1 to 2. Go back to the picture. This number must be minus 1. This number must be 2. So we're going to integrate from minus 1 to 2. As I said before, we do bigger function minus smaller function. The bigger function was 2 minus x squared, and the smaller function was minus x. So our integrand is 2 minus x squared minus minus. And then it's just calculating an integral. I'll leave it for you to check that this is 9 over 2. Another example. Find the area bounded by y is equal to the square root of x, y is equal to x minus 2, and the x-axis for x greater than or equal to 0 and y greater than or equal to 0. In other words, find the area which is shaded blue and red in this picture. We're going to do this in 2 steps. Step 1, we're going to calculate this blue area. Step 2, we're going to calculate this red area, and then we're going to add these 2 numbers together. First, let's look at the blue area. Oh, I'm getting ahead of myself. First, we need to know, where do these 2 graphs cross? In other words, what is this number? They cross when the square root of x is equal to x minus 2. This function gives us 1 or 4. Go back to the picture. 2 is just here. So what is this number? Is this 1 or is this 4? Common sense says this must be 4. In terms of the equations, if we use the number 1, square root of 1 is 1, but 1 minus 2 is not 1. So it can't be 1, it must be 4. Now we can calculate this area. We have the blue area plus the red area. For the blue area, you can see from the picture, this is just the integral from 0 to 2 of the square root of x. For the red area, now we know we're integrating between 2 and 4. We do bigger function minus smaller function. The bigger function is square root of x. The smaller function is x minus 2. And then the rest of this slide is just the calculation, which I leave for you to check. You can check that the total area, which is shaded blue and red, is 10 over 3. And then we come to the end of this course. Are there any questions on today's lesson or the last 2 weeks? Okay, so question 3 is, it's a substitution. We need to start by choosing a u. So we look at our integrand, and we need to choose a u. There's a 5 sine x here, and there's a 3 plus 2 cos x here. One of these is going to be u. And for us, it's going to be 3 plus 2 cos x. And then you copy the examples that we've done today. You need to calculate du is equal to du dx. You need to change the limits of integration. Instead of minus pi over 2 and 0, you need to change these into values of u, and then you calculate it and get the answer. So have a go at this. Have a look at the examples we've done today. Try this out and see what you get. If you're still unsure, then you can ask me again. You're welcome. No, you have to study the whole course. You might guess that because I've already asked some exam questions on the first part, then maybe at least 2 of the 3 questions will be on the topics after the midterm, but not all of the questions are going to be on the second half of the course. I'm going to ask questions spread through the whole course. You're welcome. Good luck for the exam.